Hey everybody, my name is Taylor Sparks. I'm the editor-in-chief at Integrating Materials and Manufacturing Innovation, IMMI, and I want to tell you about this brand new paper. Just came out of our journal. It's called Machine Learning of Impact Behavior in Cold Spray of Similar and Dissimilar Metals. This work comes from researchers at the University of Arizona Tucson with corresponding author Murat Latypov. Now, this paper has to do with cold spray. You've probably heard of it. If you haven't, you can check it out. Basically, it's a way of putting down coatings in depositions. And the gist of it, not to oversimplify, but you're basically taking small particle powders, they're saying here 1 to 50 microns about, and you're putting those in the jet stream of a gas that's traveling very, very fast, supersonic speeds, between 600 and 1200 meters per second are typical values, right? And then this actually impacts with the substrate, it plastically deforms, sort of splats onto the surface, and you end up with the ability to put down films, right? So this is a relatively mature technique, been around since the 90s. So there's all sorts of pros and cons about this technique, right? You can reuse the materials, it's sort of fast, you get no shrinkage, it's really great, but it does rely on sort of plastic deformation, so it's hard to do with ceramics and things. Your substrate should also be pretty ductile. That said, even though it's relatively mature and it's been used, there are still some challenges, right? And this paper sets out to try and predict some of these things. For example, they say that they're going to use molecular dynamic simulations of particle and substrate impact as a function of all sorts of different processing parameters, like what materials are they, how big were they, what was their speed. And then they're going to integrate those with experimentally determined physical descriptors, things like melting point, density, things like that, to build machine learning models that are good at predicting the two main things they care about here, which is penetration depth and impact bond strength, right? So let's look at what they did here. So they first point out that in cold spray, this particle and substrate adhesion strength and the penetration depth are super important, but they are definitely functions of what materials you're using and different process parameters. And most studies where they do this are doing it on matched materials, where the particle that you're depositing and the substrate material are the same thing. Now, there have been some other papers, and they do a decent job of pointing out some literature here, right? For example, they point out this key paper. This one's by Joshi. Here you see that they're actually able to use molecular dynamic simulations as inputs to predict what's going to happen. But again, it's typically on matched substrates. In this case, it was for copper particles on copper substrates. Similarly, you see similar things experimentally where they'll look at sort of exploring these parameters like, is there a key velocity or is there a certain size that works best? But it is very often on these matched materials. So what they're going to try and do here is essentially build up a database of molecular dynamic simulations. And here they're showing you all the different process parameters they're interested in. They're going to have these additional physics-based features, right? These physics one, and then what they're trying to predict. And they're going to explore which models are able to predict the best and which features actually matter. So let's look at the data, right? What they're going to be using are these molecular dynamic simulations. It says we considered 49 material combinations from 7 FCC materials, so they're only looking at FCC families, right? And then they're looking at particle sizes 4, 8, and 16, and then velocities 600, 1,000, 14, 1,800, 22, 2,600 meters per second. And with this combination, they end up with 882 molecular dynamic simulations. By the way, they show you to get 4, 8, and 16 nanometer sort of particle sizes, how big of a bounding box they were using in their simulation. So here's an example of an MD simulation. It's showing you a cross section, a snapshot at a certain time, right, for different materials, right? Aluminum on aluminum, aluminum on copper, copper on aluminum, copper on copper. And for all these, obviously they can be done at different sizes and speeds so that you can pull out the parameters that you might care about, like the penetration depth or the impact bond strength. So then they introduce this idea of physics-based features, and there's a whole bunch of them, right? The energy, the velocity, the density, the modulus, the yield strength, the melting point, the hardness, all these different parameters. Now, there's lots of these, and they're sort of throwing the kitchen sink at it, knowing that not all will be important, because afterwards they're going to try and back out which ones were important. First, they're going to build a model that is able to predict the two properties that they care about. And if you've seen one sort of machine learning paper for materials, you've kind of seen plots like this before, where it's the predicted versus the observed value from the simulations, and you're exploring which models are able to capture the trends effectively. Not surprisingly, in this case, a Gaussian process regression. I was actually able to do this very effectively with very minimal error. And then it comes time to figure out which of those physics-based features were important. So there were many to choose from. Basically what they did is they built many, tens of thousands of Gaussian process models, and they gave them a subset of the available features, up to 16, I think, right? And so as they gave it a variety of different ones, they could see which ones improved it or degraded its performance over time. So here you see the output of the cross-validation with all these different Gaussian process models, and it's showing you, and then as you start with just one feature and add 2, 3, adding up to 5 or 6, how much your validation score goes down, right? The root mean square error. Basically, you see that by the time you get to 5 different features, in a lot of cases, you're already not doing any better in your best case scenarios. But I like that they showed you the spread of the different values that were important. Ultimately, what did they find? Well, first off, they showed that the Gaussian process regression is doing the best compared to the other models they used. And then when it comes to the features that mattered, they show that mass, density, velocity of the particles, yield strength, bulk modulus were all the most important physical parameters when it came to predicting penetration depth. And then velocity, Young's modulus, speed of sound, and the mass of the particle, as well as the bulk modulus and the speed of sound of the substrate, were the most relevant for the bond strength. So you can check out the rest of this paper. By the way, they've got their data available from the Materials Data Facility. You can check it out for yourself in the latest issue of IMMI.